All right, welcome to the second section of Chapter 7. And today, instead of graphing exponential equations, we're going to be focusing on solving them and talking about different techniques that we're going to use to solve exponential equations. We're going to build on these techniques the rest of the chapter, so it's really important that we remember what they are and how they work. So the vocabulary you should look for as we go through this section is exponential equation, compound interest, and exponential inequality. Okay, so here's the first important property that we are going to be dealing with in this section. It's the property of equality for exponential functions. So first of all, notice we have some conditions. B has to be positive, so greater than 0, and it can't be 1. So if b is positive and not 1, then b to the x is equal to b to the y. Notice the base is the same in both of these situations if and only if x is equal to y. Right? That makes sense. If the bases are the same and I'm saying they're equal, then the exponents have to be the same. Otherwise, they wouldn't represent the same number. So here's an example. If 3 to the x is equal to 3 to the 5th, then x has to be equal to 5, right? If this is 3 to the 4th, it can't be equal to 3 to the 5th. Right? If x is equal to 5, then 3 to the x is equal to 3 to the 5th. So notice the same bases here are super key. And in an exponential equation, just a reminder that the variables are in the exponents. That's how you identify an exponential equation. All right, so let's take a look at this first example for solving. We have the equation 3 to the x equals 9 to the 4th. Right now, I cannot say that x equals 4 because my bases are different. I have 3 to the x equals 9 to the 4th. So what I'm going to try to do is figure out a way to rewrite my bases so that they are the same. So I know that 9 is 3 squared, right? Okay, so 9 is 3 squared. I rewrite it like that. So now I have 3 squared to the 4th. So that gives me 3 to the 8th. So I have 3 to the x equals 3 to the 8th. Notice my bases are the same. That's the key here. So that means that x has to equal 8. If the bases are the same and they're equal, then the exponents have to be equal as well. All right, let's take a look at the next example. Here I have some exponents that look a little bit more complicated, but it's still the same process. Here 2 is my base. Here 4 is my base. Is there a way to rewrite 4 so that it has the same base as 2? And of course there is, because 4 is 2 squared. So notice I just replaced 4 with 2 squared. And then from the property of exponents, I'll take 2 times 2x minus 1 because I have a power raised to another power. So notice I had to distribute 2. I took 2 times the whole power 2x minus 1. So I got 4x minus 2. So now I have 2 to the 5x equals 2 to the 4x minus 2. And I can set my exponents equal. If the bases are the same and it's equal, then the exponents have to be equal. So 5x equals 4x minus 2. And then I subtract 4x from both sides, and we get x equals negative 2. All right, now it's your turn to try. Try this one. Okay, your answer here should be B, which is 9. All right, and here is the work for how we got there. So notice there's 2 ways I could do it. I can either rewrite both with a base of 4, so I can leave this side as 4 to the x and rewrite 64 as 4 cubed, or I can rewrite both of them with a base of 2. Either way, we get x equals 9. Okay, now I want you to try this one. Okay, the answer to this equation should be A, which is x equals 1. And here's the work for how we got there. So in this case, I need to have both sides with a base of 3. 9 can be rewritten as 3 squared. Distribute that 2 times 5x minus 4. So I get 2x equals 10x minus 8. Subtract 10x from both sides and then divide by negative 8, and we get x equals 1. All right, now we're going to take a look at a word problem. Notice what we are doing here is writing an exponential function. So when they ask you to write an exponential function, you should come back to this example. It says, in the year 2000, the population of Phoenix was 1,321,045 people. By 2007, it had grown. It was estimated at 1,512,986. We're going to write an exponential function to model their population. X, notice, is the number of years since the year 2000. All right, in order to do this, we have to analyze what we have. So the beginning of our timeline is 2000. At the year 2000, x is equal to 0. Because they're telling us that x is how many years have passed since the year 2000. So 2000 is like our starting point. And this is our population, right? That's our starting population. The starting amount, remember, is the y-intercept, right? When x equals 0, the population is this. So I have this ordered pair, which is my y-intercept. So that's going to be very useful to us in writing our equation. Then I have another ordered pair here. When x is equal to 7, y 7, because in the year 2007, 7 years have passed since the year 2000. And our population is 1,512,986. So we're going to substitute those into the general exponential function, and we have to solve for our base, because what we don't know is the value of b. So remember, this is our general exponential function. Y equals a times b to the x. A is always our y-intercept. Okay? What we do not know is b. So we're going to plug in. Be careful what you plug in where. My y-intercept goes here, right? And then notice, remember I had a second ordered pair where x equals 7 and y equals 1,512,986. So you plug in your second ordered pair, x and y, and the value that they give you for the y-intercept always goes in for a. We need to solve for b. So we're going to divide both sides by 1,321,045. That gives us 1.145 is b to the 7th. Notice we're approximating because I had to round off my number. So in order to get b by itself, I have to take the 7th root of each side, which you will use a calculator to do. And that gives me that b is about 1.0196. So now I can write my function because I know my b value. My b value here goes in here. So again, a, this value is always my y-intercept. Oops, sorry about that. That's always my y-intercept. This is my b value, and I leave x and y as variables because they represent any x value that I would put in would give me a certain y value. They represent all the ordered pairs. So I want you guys to look at part B now. It's asking us to make a prediction based on our model. We're going to predict the population of Phoenix in 2013. Well, remember, x is the number of years since 2000, so in this case, x is going to be 13. Here's the equation I just wrote. This is the model that I wrote based on my information. And I'm just going to plug in 13 for x, and then we'll use a calculator to solve, and I get about 1,700,221 people. All right, I want you guys to try this one. See if you can write a modeling function. Okay, you should have gotten here D is your answer. And this is basically how you should have set up your equation to start solving. A, your starting value, your y-intercept is 9,426. And then you have another ordered pair that in the year 2007, x equals 7, my y value, or my population, was 17,942. So you plug those in, and when you solve for b, you should have gotten 1.0963. All right, try this one using your prediction equation. Okay, in this case, you should have gotten A, 28,411. You should have plugged in x equals 12 to the equation from the first part of the example. All right, let's look at compound interest. This is not a new topic. This is something we looked at in Algebra 1. But remember that you can calculate compound interest using this formula. The total amount of interest, which is A, or not the total amount of interest, but the total amount of money in your account, which is A, is your principal. P is the starting amount that you invest, times the quantity 1 plus R over N. R is the interest rate as a decimal. N is the number of compounding periods per year. So if you compound yearly, N is 1. If you compound monthly, once a month, that's 12 times a year, so N would be 12. And then T is the number of years. Compound interest, remember, is interest that we pay on the principal, on our starting amount, and any previously earned interest. So they calculate the interest based on the total in your account. So your interest earns interest. So let's take a look at this example and try it out. An investment account pays 5.4% annual interest, so that's R, compounded quarterly, that's 4 times per year. If $4,000 is placed in the account, that's my P, that's how much I start with. find the balance after 8 years, which is t. So we're just going to plug those things into our formula. We want to find how much is in the account after a total of 8 years. We're going to use that formula. Again, make sure you write out what you know. Notice that R is not 5.4, it's 0.054 because I have to change from percent to decimal. And then we're going to solve. Here's our formula, so we just kind of have to plug and chug. P, it's 4,000, how much I started with. R, my interest rate. N is 4. Compounding quarterly means 4 times per year. And then my exponent is n, which is 4, times t, which is 8. And then we're going to use a calculator to solve that out. We get $6,143.56 after 8 years. So my investment of $4,000 grew by $2,143.56. And if we check, if we were to use a graphing calculator, here they're showing me, I graphed the equation, I graphed my compound interest equation using t as my x value. And if I look at what happens when x equals 8 or when t equals 8, I would see that I would get the same y value. So we can confirm that with a graph. All right, you guys try this one. You should have gotten $7,960.43. And this is how the setup of your equation should look. Here's your principal. There's your interest rate as a decimal, how many times you're compounding per year, and then here is the time of 6 years. All right, last part of this section is inequalities with exponential functions. So up until now we've been doing exponential equations. Notice that the compound interest formula is an exponential equation because our variable t, which is usually like our x value, is in the exponent. So when I have inequalities, it works basically the same way. If b is greater than 1, so my base has to be larger than 1, then b to the x is greater than b to the y if and only if my exponents maintain that same inequality. X has to be greater than y. It works the same way for less than. b to the x is less than b to the y if and only if my exponents maintain that same inequality. X is less than y. Again, notice the key here is rewriting with the same base. So if 2 to the x is greater than 2 to the 6th, then obviously this exponent, x, has to be larger than the exponent of 6. Otherwise, 2 to the x wouldn't be bigger. So let's try an example and see how that works out practically. So here I have 5 to the 3 minus 2x. Again, remember this whole thing is the exponent, okay? Is greater than 1 over 625. So what you need to notice here is my base 5, well that can't be written a different way. So I'm asking myself, can I rewrite 1 over 625 with a base of 5? Or basically, is 625 a power of 5? Your table of common roots from chapter 6 will probably come in handy sometimes here if you forget. So here's our original equation. And notice 1 over 625 they rewrote as 5 to the negative 4. Why? Because 625 is 5 to the 4th. So I really have 1 over 5 to the 4th. How can I rewrite that as 5 to the something? Well, remember that negative exponents mean reciprocals. So 1 over 5 to the 4th is the same as 5 to the negative 4. So because my bases are now the same, and I know that the left-hand side is greater than the right-hand side, I can apply that same inequality relationship to my exponents. 3 minus 2x has to be greater than negative 4. And then we solve. Subtract 3 from both sides. And then I'm going to divide by negative 2, which means we'll switch the direction of the inequality. And we'll get x is less than 7 halves. X is less than 7 halves. Okay, so I want you guys to try a similar one. Try this one. Right, x is less than 3 is what you should come up with. And this is what your process should look like. Rewrite 243 as 3 to the 5th. So 1 over 3 to the 5th is 3 to the negative 5th. Then I can drop my bases and apply the inequality to my exponents. Subtract 4 from both sides. And then notice when I divide by negative 3, I switch the direction of my inequality. So I get x is less than 3. All right, that's the end of this section. And in class, we will do lots of practice.